we started looking at this yesterday. This is one of those where we're trying to use the error formula for the trapezoidal rule. We want to find what's the value of n? What's the minimum number of trapezoids we would need to get that kind of precision, right? We want to have an area less than what is that, 100,000? 1, 2, 3, 4, yeah, 100,000, okay? And so we just apply the formula. Obviously, what's A? 0, B, 1. Okay, and so this part's, pretty straightforward, but this is obviously the part that's going to be the toughest to deal with, right? Remember what that means. We're trying to find, on our interval from 0 to 1, we need to find the maximum of the absolute value of the second derivative, right? So let's finish that up. How are we going to do that? Okay, so we took there's our function, cosine x squared. What does that imply? If the squared is there, what does that imply? You gotta be clear on this. The x is squared. Good. So the implied parentheses are there, right? Okay, so we'll differentiate once. This is just a chain rule, right? So we got layers. We have cosine, derivative of cosine hand is what? Negative sine hand. Okay, times the derivative of hand is 2x. So we'll pull the 2x out front with the negative, and then we've got our sine of x squared, right? Okay, so when we calculate our second derivative, now, what do we got there? Let's go ahead and just partition this. We could pull the negative 2 out front. I'll take a slightly different approach with this. This is what I do a lot of times in practice, is I'll just plug in a situation like this, I'll just plug the constant, plug that into the factor that's got the power of x. Okay. Either way is fine, but this is how I would do it, for what that's worth. Not that that's the only way to do it by any means, but so we've got a product rule here, don't we? Right? I've got a negative 2x times a trig function. So when we differentiate, what's the first rule we got to apply? If you're thinking about just differentiating this. Good. Okay, good. So the product rule for differentiation, right? Good. So then what's that going to give us? Okay, so there's first factor times, okay, good, derivative of the second. Good. Now, so that means when we do the derivative of the second, that's going to be a chain rule deal, isn't it? Right? The derivative of sine hand is, okay, good, it's going to be cosine hand times the derivative of hand is 2x, right? Good, and then we're going to go plus second times, what's the derivative of negative 2x? Negative 2, okay, good. So we end up with, if we put all this stuff together, let's put the positive, they're both negative, aren't they? So we get negative 4x squared cosine x squared minus 2 sine x squared. What can we do to that? Anything? Good. We can pull out a negative 2, right? So we're going to get negative 2 times...
It's just 2.
Wait, could you pull out a 2x
squared?
I can't, because there's no x squared in this one, right? That x squared is inside the trig function, so it's inaccessible. So we'll pull out a negative 2, leaving us with what? 2x squared cosine x squared plus sine x squared, okay? So there's our second derivative, right? So we want to find the maximum of the absolute value of that. Now what's important here, which you can't lose sight of on this, is that it's the maximum on our interval, right? So we're looking at the interval from 0 to 1, right? Well, from 0 to 1, let's think what what a cosine function looks like and a sine function looks like, right? Because obviously we're in radians here, we're asking the question in terms of radians. So if you're to think of a cosine function and a sine function of x squared, what's the cosine of x squared? I mean the cosine of 0 squared, sorry. 1, okay. Sine of 0 squared, or 0 is 0. What about x squared? Well, that's just 1 squared, right? What's the cosine of 1 and the sine of 1? Who knows? But think of it in terms of we could even think of it in terms of unit circle if we want to, that's fine. Or we could think of it in terms of what the graph of the function looks like. So let's take a second and just think about that. So if we're going to graph y equals sine x squared, what's that look like from 0 out to 1? Well, don't worry about the x squared part for a second. Let's just graph the sine function and then figure out what that looks like in terms of, where it's going to, what part of that cycle is going to be, for example, where it gets to its peak. Because doesn't a sine function do this, right? Okay, what's the angle you're feeding a sine function up here at that peak? The height of the function is 1, but what's the angle you feed it there? In order for the sine to equal 1, think unit circle. Pi over 2. Yeah, right. That's where, up there is where we get the coordinates 0, 1, right? At pi halves. Okay, so this has got to equal pi halves. Well, what's creating the pi halves? That's the x squared, isn't it? So when is x squared equal to pi halves? What would I do to solve for x? Square root it, sure. So I'm just going to end up with square root of pi over 2. So pi over 2, just give me a sense of what that's going to look like as a decimal. 1 point something, right? 1 and some change. Okay, so if we're stopping at 1, our interval only goes from 0 to 1 for x, right? Which is the number we're feeding into here. We're stopping at 1, then where is that going to be relative to this curve? That's at 1 point something, right? Everybody agree? So it's going to be back here somewhere, isn't it? Right, see what I'm saying? So this is the part of the sine function that we're looking at. Now that's being multiplied by x squared, but it's going to give us some idea what this thing is doing, right? If I'm multiplying it by x squared, what's that going to accomplish? When x squared is 1, it means it's going to be clear up there, but when x is less than 1, I'm just going to be multiplying by some decimal less than 1, and all it's going to do is drag this curve down a little bit. But we know it starts there and ends there for sure on that interval. Question?
Wait, so you just put 1 for x and 1, or would you bring it to
How did I find that?
Yeah.
Well, because, so on the, if we're looking at the behavior of, let's take this one step further and let's look at the behavior of, y equals x squared. Is it x squared sine x we're looking at here? 2x squared. Oh, never mind, I'm looking at this one. Yeah, sine x squared. So so there is sine x squared right there, right? Sine x squared is going to look something like that. It's going to increase sort of like a sine curve, but it's never going to even make it up to the first peak. The fact that the x is being squared in there, I mean, what do you think that's going to do to the function? It's not really that important, but this is good to kind of go back to just powering through and thinking about what functional analysis would look like. The sine doesn't care where you're generating the angles from. All it's going to respond to, you feed it angles, and it's going to spit out a sine curve, right? What are the angles coming from? Well, they're coming from the function x squared. So think what that's going to do. From 0 to 1, it's going to look fairly normal, but from 1 to 2, x squared is going to vary between 1 and 4, right? Between 2 and 3, x squared is going to vary between 4 and 9. Between 3 and 4, it's going to vary between 9 and... So it's just accelerating the pace at which you're feeding that sine function angles, right? So what does that mean then? If I'm plugging in something like x equals 5, if I just went out here to 5, the sine function would have already seen the angles 0 through 25, right? So as we move further out there, what's that doing to the sine function then? Go ahead. What do you think? It's shortening the wavelength. Yeah, it's compressing the function, isn't it? Right? Between 5 and 6, when we pick x values between 5 and 6, that's feeding the sine function angles between 25 and 36, right? 36 minus 25 is 11. Well, what's 2 pi equal to? 2 times pi is like 6.28, right? So in that one increment right there, you've gone through 11, I mean, you've gone through almost 2 complete cycles, right? So what's that look like then? We don't know where it started at that, but assume it just started right there. It probably didn't, obviously. But that means you've got to go through that much between 5 and 6, only it's not linear, because as you move along the x-axis, the square keeps getting bigger and bigger at an increasing rate, right? And so the further to the right you move, the more compressed that function is going to be, isn't it? Right? So can you kind of get a sense then of what this curve is going to look like? It's going to start off looking pretty normal, but then it's just going to get faster and faster and faster as you move along.
Does it look like that in the order?
Say it again.
Does the sine squared look like that in the order?
Yeah. Well, what's the sine of 0? 0, right? So you know that when I plug 0 in for x, I'm getting 0 for y. So it does go through the origin.
Yeah,
right?
but like, does it just go like up like that?
It's going to do, well, if I'm not looking at the absolute value, if I'm just looking at the sine curve for a second, right? Here's what it would look like then, right? Whoops. It's going to look like something, and we can graph it and see, but you can kind of get a sense. It doesn't have to be perfect. You just want to get an idea of what the behavior is going to be like. Before I take the absolute value, when we go out to the square root of pi halves, is where the function's going to see pi halves. That's where it's going to be at 1, isn't it? Right? So it's going to do something like, oh, that's bad. I got to do that again. That's embarrassing with that. So it's going to go like that, right? Essentially. I mean, it's very imperfect, but you get the idea, right? Okay. It's like a child had a tantrum on the floor, right? And so if we're only, my point is just this though. If we take the absolute value of that, that part of it's just going to get reflected up like this. It's just going to bounce off the x-axis. So it would have gone, instead of coming down to here and going back up, or instead of continuing underneath the axis, it just would have bounced up. This would look like that, right? Do we even really care about that? Ours is pretty simple though, because we're just going from 0 out to 1, which is there. 1 is less than where that first peak is. So that part of the function is monotonically increasing, right? Okay, let's look at the other part of the function. So the other part of the function is this part, right? The 2x squared cosine x squared. Okay, so let's look at that. Oh, spider crawling on my board. So between 0 and, what's the cosine of pi halves? 0. Okay, so cosine of 0 is 0. So this one's starting off at 1. And if we're going to go out to, whoops, the square root of pi halves right, is where this thing would manage to get down to the x-axis. And if I kept going with it, and I'm just graphing only the cosine of x squared part right here, right? So this one would look like that, right? But we don't even get that far. We only get down to 1, which is less than the square root of pi halves. So we're only going to get from there down to about there. So what happens then if we tweak that thing by instead, we'll graph this one in yellow, if we write y equals x squared times cosine x squared. Between 0 and 1, what does x squared look like? That's pretty easy, isn't it? That's just a parabola, right? Just looks like that. So if I'm going to multiply the value of the function by these values, right?
Yeah.
What's that mean? Well, 0 times, I'm just going to end up pushing this function down by those amplitudes, right? When I get out here to 1, I get a height of 1 is the value of x squared times the cosine of 1 is, I don't know, it's just some value, some small positive value. But at 0, I'm going to have 0 times 1 is 0, right? So what's that going to cause this thing to do? It's just going to cause it to do something like that, right? Okay, so now if I subtract those two things, what am I going to get? If I take this value minus this value, the orange value minus the yellow value, and is the yellow value times 2? I can't remember.
It's 2.
It's 2. Okay, so we're going to double it. Okay, so it's always going to be, you kind of see where we're going with this a little bit. It gets complicated, doesn't it? Right, there are these two parts to it. So now, if we get this function back, we're going to take an absolute value of this function, right? And we want to analyze where it's at a maximum. If your brain's starting to hurt a little bit by trying to analyze all these things graphically, I get it, right? It starts to be, if I multiply this thing by 2, what's it looking like then? Well, it's going to raise this point up. I don't even know what the cosine of 1 is, but it's going to be twice as big as it was before. Now you're going to subtract the orange one from the yellow one from the orange one, right? What are you going to get? I don't know. At that point, it starts to be pretty hard to just, it's not very clear cut. It's pretty hard to just go up here and do some quick calculation and think your way through this, because I don't know. I don't know if that's going to end up being bigger than that or not, right? Is it going to end up having a negative value that's bouncing off of there? It's starting to get too hard to do. So what's our recourse then?
Graphing calculator.
Graphing calculator. Yeah, we'll just put this in a graphing calculator and see what we get, right? So let's use Desmos. How could Desmos have even probably made this a little bit easier? Well, we could have on Desmos. What's that? So if there's f of x, right? So on Desmos, we could just graph well, let's do this both ways. We could just graph our second derivative that we worked so hard on, the absolute value of the second derivative. So let's just call this g of x. The absolute value, so, I thought you could do that. Oh, maybe you can't.
It's shift backslash.
Shift backslash. Oh, that's nice to know. Oh, yeah, because then it gives you I got you, that's good. Okay, so absolute value of -2 times, what do we get? 2x squared cosine x squared. Keep going. What did I do there? Oops, got to go inside there. Okay, minus, oh, plus
Sine x.
sine x squared, okay. Okay, are we in the right mode? I think we are. We're in radians, yeah, okay. So that's kind of, I mean, that gives us an idea, right, that we're sort of on the right track between 0 and 1. So let's go ahead and add the other line, x equals 1. So to see this better, let's go into the graph settings and let's tweak the x-axis. We don't need to go from negative 10. Let's just go from negative 0.5 up to like 1.5, how about? Okay. So there's the function that we're looking at. Well, where is its maximum going to be? Looks like, well, okay, that's the value, but it looks like it's occurring at 1, right? Now, we don't really want to, oh, is it, you know, it looks like the maximum might be a little bit to the left of that. Very slightly. Huh. How about that? How about that? Let's zoom in on that. I think that's the case. I think that's the maximum right there, 3.845, and if we go there, we get 3.844. Okay.
Are you still imagining?
What? Okay.
But I did it on my account.
There's an artist that paints flowers and then it looks like the anatomical organ vagina.
Okay, this is being recorded right now. Yeah, it really is. Yeah. Yeah.
And you can never really hear the class anymore.
Okay. Okay. So, how could we have done this then? This ends up being, I think the book actually got this one a little bit wrong because I think it did. I really think it did because I think they assumed that it was at 1 and it was very close to 1, but it wasn't actually at 1. So how could we have done this without even having to go through the hassle of calculating the second derivative? Use Desmos, yeah. If we let f of x equal cosine x squared, then we could say that, call it h of x equals f double prime of x. So I can just go prime of x. And if we graph h, where does that show up on there? Is it?
There it is.
Oh, we didn't do absolute value. Oops. There we go. So now they do. So what's that tell you? So at least we did the math right. Okay, but if we want to find the place where the maximum is, there it is. So what's our maximum? 3.845, right? Okay, that's what we got to use for our maximum value.
Wait, when we take the maximum, it's always.
Yes, yeah, the maximum of, look up here. They want the maximum of the absolute value of the second derivative, right? So when you talk about the maximum of a function or any value of a function, you're talking about the output value, right? Not where it happens, not the x value, okay? So it's happening at this weird place at 0.9941. Who knows what kind of bizarre square root that is, right? And so this is just a numerical process anyway. So we would just use the 3.845. That's not very accurate though. So maybe you'd want to do it on a graphing calculator to get a little better. I don't know. Does the graphing calculator give you a more accurate answer than that though? It does, even on the graphing part. It does. let's resolve this issue right now and see. Okay, this is also good to know how to use your TI-84 to do stuff like this, because you can. So we could say, if we graph, I think you can do this, can't you? Maybe you can't on 84. No, you can't. It won't do the derivative, I don't think.
You have to write out the derivative.
Yeah, you would have to write it out. Okay, but that's all right. We already did the derivative, so that's fine. We can put ourselves in the right mode. Okay, we're in radians mode. And there's our derivative function right there, right? So we would just graph y equals oh, why is that so big? Good, yeah, so with absolute value. So remember we do that, the shortcut to that is just math,
Go to the right plus.
number, absolute value. So absolute value of -2 times the quantity 2x squared cosine x squared. Close the x squared plus sine x squared, close the x squared, close the quantity. I think that's it, right? And so let's set our window to go from, what did we say, -0.5 to 1.5 by, well, by ones. And then y, if we go from -1 to 4, would be good. Okay? Oh, great, what did I do? Somebody see what my mistake was? Oh, that's a minus sign, it needs to be a negative sign. There we go. Okay.
Why doesn't it just accept the minus sign as the negative sign?
Why doesn't it just accept the, oh, I don't know. 'Cause I think it treats one as an operation, I think. Yeah, yeah. Okay, so now we want to just find, let's go ahead and find the maximum. So on our calculator, we would go second calc max, and we'd go from, I don't know, there's fine. Left boundary 0.5, so hit
You can
enter.
actually type in 0.
Right boundary, yeah, you could type in 0. We can see on the graph though that that's fine. Right boundary, let's say 1. And it tells us guess, we'll just say,
Center.
you can probably just hit enter, yeah. It's gonna think for a little bit. And so it does give us a little better answer, doesn't it? Gives us 3.8448801, okay? So we'll use that. So let me take a picture of that.
So when you get something different, if you just plug that.
Oh, what'd it do?
in there.
Oh, I know what it is. What's your question?
No, I figured it out.
Okay. There it is. Okay, so then if we wanted to finish this problem up, I mean, we had to, unfortunately, we had to rely on the graphing technology to do this one. I mean, we could have probably done this, but it would have been pretty tough, right? The trig would have been pretty hard. If we wanted to maximize that function, this is what the graphing calculator gave us. How could we do this using calculus? What would that involve? A calculator. That's a good answer. But if you think back to, I mean, we've done a lot of maximization. That's just one type of optimization, right? How would we, if this is the function that we're trying to maximize on our interval, then if we were going to do this analytically, because we don't want to necessarily have to do this, I at least want you to see that there is a recourse. There is an analytical recourse here. It's just maybe not a very good one. We could just call this g of x. That's the function that we're trying to maximize on our interval. Now, one thing we did get from the graph, though, is that this function is, it's always positive. Or was it? No, it wasn't, was it?
For the interval.
If we look at, let's go back for just a second. Actually, it wasn't. If we take this out of absolute values, let's call this j of x. Just copy that part.
Why do we always use f of x?
I don't know. Why do we always use x? You know, it's just kind of what we've, the convention we've adopted. So what we can see here is that between 0 and 1, the actual function is always negative, right? And then when we took the absolute value, we just reflected it upwards, just bounced it up, right? Okay, so this would get a lot easier for us to deal with if we didn't have to use that darn absolute value. And so really all we're going to do is take the opposite of this, which just makes that 2 positive, right? So for our purposes, as long as we're staying between 0 and 1, our function that we're trying to maximize is just positive 2 times that whole thing. Right? Okay, so if we wanted to do optimization on this, we'd make a table. What would we do?
You'd send it zero.
Set what equal to 0?
Get the derivative.
We'd have to differentiate that and say the derivative equals 0 to find the critical numbers, right? That's going to be, it's going to be kind of a mess, isn't it?
Do you see what we did?
What's that?
We have to do this problem. It doesn't get like one done in a period.
Oh, that's the way it gets. I mean, honestly, math gets to a point where you couldn't even begin to do a tenth of a problem in just one measly 45-minute period. But it's, so it's,
And yet you give us 4 assignments?
yeah. So, I mean, we're going to take the shortcut here, but that's really not the point I want to make here. Is that you could, I mean, you could, if you were going to sit down and you didn't have 7 classes to do, and you were really focusing more on math, like maybe some of you'll do in college. This is a problem you could do. You know what the roadmap is. You would just have to differentiate this, and you're going to get something kind of ugly. But then you're just going to find the zeros of that derivative. And what would your answer have been? You would have found one. You would have found 1 0 at x equals that number. What is that? Why do we get that decimal? I don't know. It's going to be some, who knows? I mean, when we solve this thing, we're going to end up getting some crazy square root of this over square root of that, and it's, you know, and that's what turns out to be the 0.994, blah, 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 right? But there is a way to do this. This is going to be a pretty challenging trig problem to solve when you're finding the zeros in this thing. I mean, it really would be. But at some point, you know, if you continue with math, that'll be something that you'll be willing to maybe tackle, right? Okay, so we won't do that. We got our answer. There it is, right there. Right, this is the decimal value that we're going to plug in for the maximum of f double, the absolute value of f double prime.
Even though for y.
Say it again.
Yeah, 'cause that's as high as it gets.
That's as high, right? That's as high as it gets between 0 and 1, right? That is the highest the function got. Okay. So then that's what we would plug into our function here. And from that point forward, it really, then it's just a matter of doing a little bit of algebra, right? Just solving for n squared, or for n. So if we took this part, took this part.
Computers amazing.
Yes, they are. And the reality of doing math in, you know, in modern age is that if you're going to be an analytical mathematician, like if you're an engineer or you're a biomedical engineer or a physicist, yeah, you do a lot of math, but a lot of times, I mean, you're gonna let the technology do the nitty gritty for you. But the thing is, what you're really having to focus on is the process. Sometimes the process is the most interesting part of the puzzle. And doing the actual calculus and the algebra is just kind of cumbersome little details, right? So that enables you to sometimes bypass the little, you know, that stuff and just focus on the process, get an interesting answer. So all we'd have to do then here is solve the equation. Now, A is 0, B is 1, right? So we get 1 cubed. So 1 over 12n squared times that is less than 1/100,000th, right? So then I would just flip both sides, and we'd get 12n squared over 3.8 blah, 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 is greater than 100,000. Just multiply 100,000 times that, divide it by 12, and square root it, and I'm going to get some answer. What's my answer? There's the results. So let's do a new one. So 100,000 times. Oh, I got to go back here and do it, don't I? I need to grab that number. Oh, I'm just going to write it in. Times 3.8448801, all divided by 12, and then I'm going to square root the whole thing, right? Okay. And it gives us 178.999999. So how many do I need? 179, right? I have to have at least 179 trapezoids on that one. Okay? Right? Make sense?
Yeah.
Yeah. So that's one you got to use. You got to use graphing. That's the only. Most of them were pretty easy to do, and I wouldn't give you one like that on the test for sure. Right? Most of them you can look at them and say, okay, well clearly you can see that the fraction's going to be, that represents that weird absolute value of the second derivative. It's going to be maximized when the denominator's minimized, and so you can kind of think your way through them. This is one where you couldn't, right? This is real math, though. I will never forget my nightmare assignment from hell in college in quantum mechanics, where I ended up in a one-week problem set. It was like, ended up being over 100 pages of math for 4 problems, easily. I should bring it in. I've still got it at home somewhere. But that's what it was. I mean, it can, you know, math can be big.